we've wrapped up talking about logic in chapter one. Historically, my students are generally they're kind of tired of not seeing numbers in their math class by the time we get to the end of our stuff on arguments and logic. Good news if you're in that camp. What we're going into now, I've got you covered as far as numbers are concerned. I am going to fill your boots with numbers over the course of the next chapter. So, chapter 3, where we're headed now, is talking about what we call probability. So, I think on some level, most students, when they come into Math 107, have some idea as to what I mean when I talk about the probability of an event's occurrence. I'll go ahead and sort of lay the groundwork here, and then we'll take a look at some of the calculations going forward. So the notation you're generally going to see for the probability of an event is going to look like that. P of E. That's not a multiplication. I don't want to delve too deeply into what this means that we talk about probability as a function. Don't get too stressed over that. So a probability is, for our purposes, is going to be a number that lives between 0 and 1 inclusive. And if an event has a probability of 0, it's effectively impossible. An event with a probability of 1, you might call that inevitable. It's going to happen no matter what. So that's kind of the ground rules there. Again, intuitively, probability, how likely it is a particular event is to happen. So now, being a mathematician, I've got to take this and make it technical. That's like what they pay me for. So I need to lay the groundwork as far as definitions go. We'll be looking over the course of the chapter at what we call probability experiments. Now, this isn't like a lab science experiment where you need fancy coats or test tubes or anything. A probability experiment is basically a thing you do and then you observe what happens. That thing you observe is what we call an outcome of the experiment, and there's generally a slew of possible outcomes of whatever it is that we're looking at. We gather up all of those possible outcomes, and we refer to them as a sample space. We'll often denote that with a capital letter S, where it comes up. Some textbooks and folks would use like the Greek letter omega. I stick with S. So, and an event is basically a subset living inside that sample space set. So you can kind of envision, in some sense, when we've been talking about Venn diagrams and stuff, you can think of your sample space as being like that universal set, the box I would have drawn around my Venn diagram, and then I would have some event living inside it as like a circle inside the diagram. So Venn diagrams keep coming up in the course. So that's experiments and outcomes, sample spaces and events, that sort of thing. All right. So I wanted to take a look at a few of the classic examples of probability experiments so we can get a handle on this whole sample space stuff. So, one of the classic examples is flipping a coin. I'm not going to try to flip a coin in front of the camera for you. You don't need to watch me try to, flip a coin and then fail to catch it like a dozen times. That's, not a super productive use of either my time or yours. So, but in terms of listing the possible outcomes of a coin flip, hopefully we're all in agreement. And no silly shenanigans where you manage to flip the coin so it lands on its end, nothing like that. The coin comes up either heads or tails. So that's how I would label the sample space. You could write them out more explicitly, but that's fine. So notice the curly brace set notation comes back. I did want to go ahead and mention, let me label that as one example so I don't necessarily have to erase the board. We're going to come back and talk a fair bit about cardinalities over the course of this, so you may remember that's like a measure of how big a set is. So for this, we've only got 2 elements of the set. So our sample space, not very big, it's got a cardinality of 2. Okay? So that's one example. All right, next, another one of the classic examples, shuffle up a deck of cards and draw one out of it. So in that instance, for now, let's just suppose we leave the jokers in the deck. So this brings up a good point. If you're not familiar with the contents of a deck of cards, I tend to take that for granted. I grew up playing cards just about any time my relatives got together. If you're not so familiar with it, inside the PowerPoint slides, I've listed a couple of handy references, one of them being the layout of a deck of poker cards. Then some of the lingo and stuff is in there. You can take a look at that if you need it. Additionally, I did point out a reference to the layout of a roulette wheel and what it talks about in terms of payout odds of bets and stuff. So you can take a look at that. Like I said, we use those as sort of our baseline examples in a few scenarios, but yeah, I want to make sure you're aware that's there. All right. So coming back to the card drawing. So we shuffle up the deck. We left in the jokers for some reason or another. For the record, generally textbook problems, we don't factor in the jokers. It's usually just a 52-card deck. So if you were writing out the sample space, you've got to be a bit more particular with this. It would be pretty big because it's like, well, I've got the 2 of hearts, the 3 of hearts, on up to the ace of hearts. Then you repeat again for the clubs because the suits make individual cards different. So I'm not going to write out the full roster thing for this. I'm short on board space. It's not an effective use of recording time. You get the idea. The big thing I want to mention here is, by design, we know there are 4 suits in the deck, 13 values within each suit. 4 times 13 is 52. If we toss in the 2 jokers, we have a total sample space size of 54. So one more example I wanted to take a look at here is dice rolling. So a lot of the examples in the notes just give or in the homework rather, or in the text, talk about rolling a single die. I think rolling a pair of dice is more exciting. I do tend to specify how many sides my dice have, so spoilers in case you didn't know, dice can have more or fewer than 6 sides. So I've talked about rolling a pair of 6-sided dice. So now in this instance, if you want to list out the sample space, I like to go through this one because it's a little bit more specific, because what a lot of my students will end up doing is they look at it and they say, oh, well, my possible results are like 2 through 12, because by default, most of the time when we roll dice, we're playing a game of some sort, and we probably want the numbers added together to see how far we move on a board or something along those lines. I get the temptation to do that. It's not really an accurate way of representing everything here, because we want each of our outcomes to be what we would call equally likely to occur. So, for instance, I've got a sample pair of dice right here, and you notice they're mismatched. So let me pull the red one up a bit. So it could be, we get a 1 on the red die and a white on the 6 die. That is a different result than if I had a 6 over here and a 1 over here. I mean, we can tell they're different because of the mismatched dice, but the principle still holds even if the dice happen to be the same color. So when we track our outcomes, typically what mathematicians will do is they write it like ordered pairs, like they were plotting points on an XY plane or something like that. So we have we have 1, 1, 1, 2, 1, 3 on up. Then we would go 2, 1, 2, 2, so on and so forth. Until we get to the box colors at the very end, and we have a pair of 6s, okay? So that's what the sample space would look like. Our buddy, the fundamental counting principle, would tell us in that instance, well, if we have 6 possible outcomes on the white die, and 6 possible outcomes on the red die, then the counting principle says we multiply these together, bam, and we would have 6 times 6, or 36 possible die roll results. Again, this is taking into account that there's some kind of duplication built in there for most rolls, but we'll talk more about that in the next video. So I've tried to lay the ground rules here. As always, feel free to reach out to me with questions. Next time in another video, we're going to talk about how we actually calculate probability. So stay tuned.